In the last lecture, we mentioned that like physicists, we also care about time and space, right? In particular, we care about how long a program will take to run and how much memory we need to run the program. Okay, so the idea of order growth is that we want to measure the resource that's used by a computation process, and essentially, the time is how long it takes to run a program, and the space is how much memory we need to run the program. Okay, so we want to ask questions like the following. So suppose factorial 5 takes a certain amount of time to run. How long will factorial 10 take to run? Similarly, suppose fib 10 takes some amount of time. How long will fib 20 take? We want to know how much more time and how much more space. Okay, 2 times, same amount of time, or 4 times, for example. Formally, we will define the following. Let n denote the size of the problem, for example, Fibonacci n, right? And let Rn denote the amount of resources required to solve the problem. So R can either be time or space, right? So Rn has order of growth theta of Fn written as Rn equals to theta of Fn if there are positive constants K1 and K2 such that K1 and K2 times Fn, right, they will bound the Rn for any sufficiently large value of n. In other words, the following curve is true. It means you have two lines. One is the K1 times Fn, and the other one is K2 times Fn. At the beginning, you don't know what's happening, but basically as n goes big, beyond some number n0, then you have a situation whereby Rn is sandwiched between these two lines. Okay, so this is essentially when this happens, it means that f of n is the order of growth for R of n. Okay, the top line is called big O f of n, and the bottom line is omega f of n. So typically in this class, we will only worry about order, the big O. So the upper bound to how much takes or time or space the computation will take. Okay, so if both order n and omega n are the same, then this will be big theta n, right? So it's a tight bound. Now, intuitively, if n is doubled, right, then the resource required, whether time or space, is increased to f of 2n, right? So some common fn's are the following: 1, n squared, n cubed, and so forth, all right? Log and so forth. So let's take a look at this particular example. In recursive factorial, what happens is that your time is order of n, right? Because the time taken is proportional to n, so order n. And the space taken is also proportional to n. Remember, it's the number of pending operations, so it's also order n. Okay, this is linear and this is linear again. Next, we have the iterative process. In this case, time is order n because it still takes a n number of steps. Okay, you can see here, it takes n number of steps to finish computation, but the space now is order 1 because it's constant, right? Again, it doesn't matter what n is, it always takes up 2 spaces or two like boxes in memory to store the product and the counter. So this is linear and this is constant. So space is a constant amount, like order 1. So typically, if a computation C takes 3n plus 5 steps to complete, then what do you say about order? Well, it turns out we will drop the constants and drop the factors and just keep the n term. Okay, take out the largest term and drop the constants, right? So how about this thing? In this case, 3 to the n will dominate the other two terms. So this particular expression is order of 3 to the n, because 3 to the n is the exponential term. Okay, in this class, it's very simple. All you need to do is to identify the dominant terms, ignore the smaller terms, ignore the additive or the multiplicative constants, right? So in this case, this 4 n squared minus this thing plus this thing is order n squared because you just care about the n squared. Now, if you have this thing, then n divided by 7 plus this n log n is order n log n. Because n log n will be bigger than n at some point, right? Now, note that because log b base a is the same as log b base c divided by log a base c, so in log, the base is not important at all because the base would just drop out as a constant. This is actually a rather complicated subject, and there are other classes at NUS that you can take later that will basically teach you more about how to compute the order of growth, okay? And some will involve quite sophisticated proofs, like CS1010X and CS3230, but in this class, we're just trying to give you a flavor of order of growth, so you don't have to know too much, just know big O, and you will learn along the way some techniques to kind of estimate order of growth. Okay, for now, all you need to do is to count the number of computation steps, identify the basic steps, try a few small n, extrapolate for really large n, and look out for worst case scenarios, right? So this process we will go through in class over a few examples, and hopefully that will help you understand this concept. This is a rather complex concept, right? So many of you at this point will have a hazy idea. Never mind. Okay, bear with us. In a few weeks, we should be clarifying all these things. Okay, so here is a table showing you how the numbers grow. This is just n. The log n will actually grow quite slowly, right? N log n will grow a bit faster than n, but not that fast. Okay, n squared will grow quite fast, n cubed will grow faster, and 2 to the n is much faster. The key takeaway of all this order of growth is that there are many ways to compute something, and different ways of doing it or different algorithms can take a dramatically different amount of time or space. So this is something that you will learn to appreciate in a while, but for now, just keep this in mind. Now let's take a look at this particular function. What does it compute? Is it obvious by now? Well, the first lesson you need to learn is do not call your function foo. Just now, what I was trying to do is obfuscate a function on purpose to make it confusing. Now, if you name the functions properly, this is what you will see. This particular function is actually the power function. What it does is that it computes b to the e, right? And I shall leave it to you as homework to go through this function and see how it works. Perhaps you can take this code, cut and paste in Python tutor and run through it for some simple examples. Okay, how long does this take? What is the time requirement? You realize this will be order n. Okay, and space, it will also be order n because there'll be n numbers of different operations. Now, can we do better? Well, of course we can. So let's take a look at how we can express this particular computation. So b to the e can also be expressed as 1 if e is 0. Okay, or b squared to the power of e over 2 if e is even, or e minus 1 times b if e is odd, right? Okay, there's nothing new that we're doing here. We're just restating the definition of b to the e, right? Now, so there's this idea called fast exponentiation, and the idea is that instead of doing it the usual way, we just do what I just showed you. If e is 0, return 1. If e is even, you return the fast exponentiation of b squared to the power of e over 2. And then, if not, then you return b times fast expt b e minus 1, right? So over here. Okay. Now, what's the time requirement now? It turns out it will be order log n. Okay, it's much faster. Space requirement, also order log n. Now, why is this so? Well, we'll discuss this example like this later on in recitation. But for now, just keep this in mind and see if you can figure this out. Okay, can you do this iteratively? Well, of course we can. Why don't you try to do this? Okay, so the last lesson I want you to take away today is that count change is actually something that's rather easy to formulate via a recursive process, as we had shown you an example. It's actually much harder to write this iterative process. Okay, you can try it if you are undeterred, but it's really hard. Okay, now moral story is that in general, an iterative process is much more efficient than a recursive process in general. Okay, but sometimes it is very hard to derive an iterative solution, whereas the recursive process is much easier. Okay, so so the reason why we do both and I show you both kinds is because we want you to be equipped with skills to do both iterative and recursive, and depending on the problem, you will be able to use the right thing. Okay. Now, the general idea here is that even though recursive processes seem to be more inefficient, don't worry too much. Just write it and then leave the optimization to the interpreter, the compiler. Okay, the last thing I want to say before I finish this lecture is that it's actually easy to write code. The hard part is actually figuring out what to do, and this is the thing you need to learn in this class. Okay, so in this lesson we've learned a few things. We learned recursion, and the general thing you do is divide a problem into smaller problems of a similar shape, right? And then you basically solve it for a simple base case, and everything goes from there. And when we talk about iteration, you basically use the while or the for loops. And the last thing we just saw is the fast exponentiation technique, whereby you take a problem and you kind of divide it into two. Okay, we'll discuss this kinds of the techniques later in class. Finally, we talked about order of growth, which is really how we actually measure the time and space requirements of computations. And the key idea is that different ways of doing computations will consume different amounts of resources. Okay, so essentially, you will have to eventually pay attention to efficiency. For now, you mostly will focus on just correctness, just getting your code to run and run correctly. All right, so that's all for now. Okay, you take care and have a good week.